So this is the calculus part of chapters 4 and 5 in the calculus-based book. And there isn't a huge amount when it comes to Newton's second law. Newton's second law applies for a given instant in time. So you're not really dealing with derivatives. You're calculating acceleration, which is the result of a derivative. So I'm just going to talk about some general ideas. What would be different from a calculus-based standpoint? Well, one thing is if you have multiple forces acting on a point and you want to find the net force of these three, when you do it by components, you can say, I'm going to sum the forces in the x direction, I'm going to sum the forces in the y direction, and that gives me my resultant force in the x and y, and then I can create the resultant. From the components I can get the total vector. So one thing you might do differently is how you would represent the forces. Instead of saying, which you can represent both components in terms of the unit vectors. So let's call this F1, and we'll call this F2, we'll call this F3. So the vector F1 is going to be F sub x. So this is the vector, and then you have the components of the vector. So you get the x component, which is a scalar, times the unit vector in the x direction, plus the y component of the force times the j unit vector, and that'd be F1 sub x and F1 sub y. And then you'd have F2 vector is equal to F2 sub xi plus F2 sub y j, and the third force, F3, would be F3 sub xi plus F3 sub y j. And these would all be using the appropriate angle. So if we based it from the positive x-axis, we'd have, this would be theta 1, this would be theta 2, and this would be theta 3. Now, a lot of times we do it based on the horizontal surface, so we might take the angle between here and here, but in the strictest sense of not having to worry about signs, the F1 vector would be the magnitude or the length of vector 1, which we show as the vector, and then these absolute values type sign. That's a vector magnitude. That's a length times you'd say the cosine of theta 1 I plus the magnitude of the force vector F1 times the sine of theta 1 j. And you could do that for the second. And because the angle is being measured from the positive x-axis, you don't have to worry about the signs because they'll come out automatically. Cosine of theta 2 I plus F2 magnitude sine theta 2 j. So what will happen is, when you go to theta 2, it's a number between pi over 2 and pi. So when you take the cosine of it, it'll be negative. When you take the sine of it, it'll be positive. And then, if you want to find the resultant vector, so if you have the r as the resultant vector, you add the three vectors together. So symbolically, you'd show it in this form. And if we broke it up into, we could then represent the vectors by the components times the corresponding I and j. And I'm going to just use the form that's without the angles just to make it a little easier to do. So that's f1, and then you'd have f2, so you take f2x times the unit vector in the I direction, f2y in the j direction, plus f3 in the x direction, plus f3 in the y direction. And the way you do vector addition is you add the components together. So you get f1x plus f2x plus f3x all times I. And then the y component is f1y plus f2y plus f3y times j. And that's what we're doing when we break it up into the components and add the components together. That gives us, adding the components together gives us the components of the resultant vector. If you take statics or dynamics, you'll deal with a lot of this because they deal with three-dimensional situations. Now, the other thing that is seen a lot is, Newton's second law says the sum of the force vectors, which is the net force vector on the object, is equal to the mass times the acceleration vector. So what can happen is you can have f vector as a function of time. And as a consequence, the acceleration vector is a function of time as well. So you can either have a non-constant force or a non-constant acceleration, and you can what would a force look like that has a t time component? Well, you might have something like t squared times the I component, the I unit vector, and 2t times the y component plus t cubed times the k component. So if you wanted the acceleration vector as a function of time, all you have to do is divide the force vector by the mass. So that's just, you just have t squared over m times I hat 2t over m j hat and t cubed over m k hat. So because this is a scalar, it's a scaling factor, and you can just do each component by that. So theoretically, you could, if you knew the acceleration, then you could calculate the velocity by integrating. So in chapter 2 and 3, a lot of times we're given the displacement as a function of time, and we could calculate the velocity and the acceleration. Here, what you could do is you could specify the force as a function of time, and then you could use Newton's second law to get the acceleration as a function of time. And once you have the acceleration as a function of time, then you can integrate that to find the velocity as a function of time, and you can integrate again to find the displacement as a function of time. And that's sort of what inertial guidance systems do. They measure the acceleration. Instead of being an equation, they measure the acceleration as a function of time in 3 dimensions, and then they calculate what the displacement and velocity are, and that places it in, in a 3-dimensional world. So that is kind of the biggest differences. And you've got 4 problems that look at those kinds of situations. And that is all I think I'll have to say about that. I'm trying to remember which your screen's going to go blank, because I'm just going to look at what problems I assigned for homework, because I don't remember. So chapter 4, 41, okay. So that one is, you have displacement as a function of time, so you can take the derivatives to find the velocity and acceleration. When you know the acceleration, you calculate the force through Newton's second law. 51 is you're given force as a function of time, and they're asking you how far the object travels. So that way, that's what you're doing, is you're using force to get acceleration through Newton's second law as a function of time. Then you can take the acceleration and then integrate to find the velocity and the displacement. So that's what those two problems are. And then if you go to chapter 5, you've got two problems there. 23, which gives you force as a function of time. So it's kind of the same deal. And then 69 is you're given tension as a function of time, which is force. And then you can calculate acceleration. So that's, they're all basically taking a force, not necessarily in this form, in a simpler case. They're using that force to calculate the acceleration, which is not constant, but is actually time varying. And then you have to integrate whatever the mathematical expression is that represents the acceleration. And we gave you the rule. They're all polynomials, so you just use that rule that says when you integrate a polynomial, which consists of terms, functions, the function consists of x to some power, typically 1 or 2 or 3 or something like that. We don't typically use decimal, non-integer exponents. So the integral of this function is going to be equal to x to the n plus 1 divided by n plus 1. So if f of x is 20t, then the integral of 20t dt is equal to 20 times the integral of t. Well, t is the first power, so you add 1, and you divide by the new exponent. So the answer would be 20 divided by 2 is 10, you get 10t squared. So that is how the integration works. And I think most of them, like I said, are linear. And so in this case, this may be the acceleration as a function of t. This is actually a function of t. So when you integrate it, you would get velocity as a function of time. And when you integrate it, you get this constant, which you have to use the initial conditions to be able to evaluate that. But a lot of times they start at rest, so rest means that goes to 0. The constant is 0 if you start at 0 velocity or 0 displacement.